Okay, so let's take a look at some applications of the derivative tools that we've learned. We'll start with some very basic ones, and I'll give you a couple examples of kinematic equations, right? Equations of motion. Some particle, some card, and it's going to be arbitrary, but it's going to show you the application of applying derivatives for looking at a position equation for the position of an object and then determining the velocity and acceleration. So let's jump right into it. So the basic kinematic equation is the parabolic equation, the equation that describes the motion of a ball being thrown. In this kinematic equation, you assume that you have an initial position that's known, initial velocity that's known, and an acceleration that is constant. So in green are all constant values. So assuming this, how do we figure out the velocity and then the acceleration equations, right? So, think about what derivative tools you need, right? This one's just going to be additive. And we want to determine the first derivative, dx dt, right? So the first derivative of this full function with respect to time. And then to find acceleration, we need the second derivative, which essentially just means take the derivative of the derivative. So let's start with the velocity term here, right? So we can break out each of these components into individual derivatives, right? So dx dt would be dx naught dt, this term, plus dv naught t dt, this term, plus d1/2 at squared dt, this term, right? So we know the principle that we know one of the rules is you can break up the derivative into each individual term. X naught's a constant, so this is going to be 0. V naught's a constant, so that can come out, and we can just take dt dt. 1/2 and a are constants, so those can come out, and we could just take dt squared dt. And so our equation looks something like this, right? 0 v naught dt dt plus 1/2 a dt squared dt. Okay? dt dt, what's that? That's basically a linear line with a slope of 1. So this is just going to be 1. This is the same thing as dx dx, right? So x to the power of 1, right, where n equals 1. So this is just going to be v naught plus 1/2 a dt squared dt. This is like the derivative of x squared dx. So this is going to give me 2 times t, 2 minus 1, or 2t. So 2t times 1/2 a. So this gives me, that's just 0. V naught times 1 is V naught plus 1/2 a. Derivative of t squared dt is just 2t. So this is going to be V naught plus at. And then we do the same thing for acceleration. We just take the derivative of this term. So the first derivative of the first derivative, right? The v dt is the same thing as the second derivative of the function itself. Second derivative of x with respect to time. So if I take the derivative of this term, remember that v naught is a constant, so dv naught dt plus dat dt, right? Just breaking up these two terms into individual derivatives. dv naught dt is equal to 0 because v naught's a constant. Dat dt, a is a constant, so that can be pulled out. So a dt dt is just 1, so this is just going to be my constant a, which makes sense because if a is a constant, then the acceleration function with respect to time is just going to be a constant a. Now, what if I put in actual numbers here? What would this look like, right? Graphically can help us to visualize what's going on. So let's say my position equation is 3 plus 5t minus 10t squared. And let's assume that the position units are in meters and the time component is in seconds, just to keep things simple. So this is my x naught term, so that means we have an initial position of 3 meters. This is my v naught term, so we have an initial velocity of 5 meters per second. And this is my 1/2 a term. So negative 10 is 1/2 a. So a is negative 20 meters per second squared. Okay, if I graph this equation, we have a parabolic with some kind of deceleration going on in the system. Initial position of 3, right? This is my x graph. This vertical axis is my x. This horizontal axis is my time in seconds. So we have an initial position at 3 meters, initial velocity of 5 meters per second, and then we have a constant deceleration, negative 20 meters per second squared. If I take the velocity equation, plug in my v naught and my a terms, we get the expected linear graph of the velocity starting out as positive, decreasing past 0 at the maximum point, and then decreasing or coming back, right? So if this is x, like a horizontal position, it's coming a certain direction and then it's reversing. You could change this into a y perspective and think about throwing something up, and there's a gravity term that's negative 20, so a higher gravity than on our Earth, right? On Earth, it's about negative 10 meters per second squared. And then for the acceleration, that's just going to be a constant. So we can see how we can start off with a known position equation. And sometimes this might be something that you can actually derive, and other times you might get this equation from points on an experiment where you have intermediate points, discrete points, and then you curve fit to find this equation. Then you could back out of velocity and acceleration. In those cases, it wouldn't fall out so cleanly as it is here. So let's take a look at a couple examples where we have a starting position equation that's different than the parabolic, like throwing a ball equation. We're going to walk through the same process in determining the velocity and acceleration pieces of it. So let's take a look at our second example. Okay, for this second example, try to visualize what this function, position function, represents. We have an oscillating component, which I think we can all visualize, right? So a ball bouncing, there's your amplitude, there's your frequency components. It could be a spring, a mass spring system. And then you have a linear component, right? So this linear component is increasing. So you can think about this as something moving with a constant velocity, right? A cart that's being pushed, something that's moved by some kind of device at a constant rate. So a combination of these two is literally going to be, because they're just added together, it's literally going to be the combination of the components as if the thing that's oscillating is sitting on the thing that's moving in a constant rate. So I think this one's pretty easy to visually or conceptually think about what kind of systems, in this case position, or like a position function. But if we change this into something like temperature based or pressure based or current based or charge based, I think we can see how we have these two components from a physical perspective. So let's say that we have this, and let's say that our position is in meters, units of meters, and our time is in seconds, unit seconds. So now how do we solve for a couple things? I want to solve for the velocity and acceleration both at 30 seconds. So what we're going to need to do is solve for both the velocity and acceleration functions. Just for completeness, it'd be useful to take a look at what the position function looks like graphically, and then where we are physically at 30 seconds. So here's a graph of our position function. So you know what the oscillating sine curve looks like. If we shift the baseline so it follows the 4t line, this is what we get, right? So we basically get the sinusoidal wave and shift it so that it matches that linear curve. So if I want to figure out where we are at 30 seconds, I can plug in 30 for t here. Now, sine 30 pi seems difficult to solve, but we can solve this one in our heads, right? So first off, we know from the unit circle when we have a value in here, we're somewhere between, we can think about it as either between 0 and 2 pi, or we can think about it as some multiple of some value between 0 and 2 pi. Because if we go 0 to 2 pi, if we go 0 to 4 pi, we're just doing the loop twice. Well, we have 30 pi. So if you divide this by 2 pi, we get a round number, which means we're just doing 15 cycles. So that's the same thing as if we were just looking at sine 0 or sine 2 pi, right? And if you look at your unit circle again, remember we start the angle in the counterclockwise direction, starting from the x-axis, positive x-axis. So sine 30 pi is the same thing as sine 0. And sine 0 along the positive x-axis has a 0 y value, so it would just be 0. So it would be 10 times 0 plus 4 times 30, which would be 120 meters, right? So we can look at a graph. Here's 30 seconds, and then we're at 120 meters, right? If I want to figure out the velocity, I'm just taking the derivative of this component. We're going to need to apply a couple of things. That's why we have the table here to reference. We remember the rule that we can split a function into two parts if it's just added together and take the derivative of each individually, and we will get the total function derivative. All right, so let's think about each of these separately. So I have 10 sine pi t. I know I'll take a constant times a function that I know the derivative of, and that'll just be the constant times the derivative of that function. So this will be 10 times the derivative of sine pi t. Well, I don't know how to take the derivative of sine pi t, but I know how to take the derivative of sine, which is just cosine. I could do a substitution, call it pi t, call u a pi t or g a pi t. This is basically my chain rule. So I take the derivative of pi t dt, that's just going to be pi. So I'm going to have 10 times pi times cosine of that full function, pi t, plus derivative of 4t is just going to be 4, right? Because the constant is 4. Derivative of t is dt dt. dt dt from this function here, we know is just going to be 1. So then we get 10 times pi from that chain rule times cosine pi t from the derivative of sine x plus 4 from 4 times dt dt. So we get 10 pi cosine pi t plus 4. That's what this graph is showing us, right? This 4 is just a constant, so that's the offset for the baseline. It's not 4t anymore. It's just constant 4. So at 30 seconds, we can see we're at a peak. If I look at the mathematical component, I have 10 pi cosine pi, 30 pi plus 4. 30 pi, remember, is still just looking along the positive x-axis. So cosine, or the x component of that, is just going to be 1. So it's going to be 10 pi plus 4. Pi is about 3.14, so 10 pi is about 31.4. So plus 4 is 35.4, which graphically we see here. All right, lastly, the acceleration. Acceleration is the second derivative of the position function, or the first derivative of the velocity function. So we can take a look at this velocity function and take the derivative of this. So we get 10 pi as my constant, then we get multiplied by another pi from the chain rule, and then derivative of cosine term is negative sine. So then we'll have a negative multiplied by a negative sine pi t. Derivative of a constant is just 0. So we get negative 10 pi times pi, or pi squared, times sine pi t. That's what we have here. And at t equals 30 seconds, we're going to have a sine 30 pi term right here. So that's going to be 0. So we expect to see 0 right there because it's crossing the x-axis. So it's great. So let's take a look at one more example problem and have you work through it on your own, and then I'll walk you through that process as well. Okay, so here we don't have an oscillating component. I define it as position, but you can think about this as any kind of property, right? We have a decay component. E to a negative something t or e to a negative something x tells me you have a decay. The rate of decay, the speed of decay, is indicated by the value shown here, right? A larger value here, right? A negative larger value would give us something that would, like a -5, let's say, would decay at a faster rate. The +3 right here is the asymptote value, the horizontal asymptote. Without it, you can see that if t approaches infinity, that this whole term will go to 0. With it, you have an offset and decay to the 3 value. So you can probably visualize a lot of physical systems where you have this exponential decay, right? A good non-position example is temperature, right? If something is hot and it's cooling down, it's going to cool down a lot faster initially, right? There's a bigger change initially, and then as it gets closer and closer to whatever the environment, the room temp or a water bath temperature is, it's gonna change slower and slower as it gets closer and closer to it. So this is a good example of that. Now, if I want to know the velocity and acceleration, I just take the derivative like I saw earlier. So we can graph this position function here, right? So we see the decay. Even without solving it, we know generally what this will look like because I know my exponential decay derivative from a few videos ago. Can you think, just looking at the slopes, right? Is this a positive or a negative slope? Is the slope changing, increasing or decreasing? So we can already think some pieces of this without actually solving the mathematical components of it. But if we did solve it, this is what? The constant c again times the derivative of this term. Again, we can use chain rule. The chain rule will tell us negative 0.05 times e to the negative 0.05 t times 40. Derivative of constant 3 is just going to be 0. So our velocity graph, right there's my constant c. Here's the chain rule component derivative of my exponential right there, and then multiplied by e to the negative 0.05 t. So I get -2 times e to the negative 0.05 t. So we have a large negative value initially, as we see the large slope right there, and then asymptoting itself to 0, which is representative of when the position function is basically at 3, not changing, right? So if it's not changing, the velocity is going to be approaching 0. Then the acceleration component, the velocity is getting larger and larger, right? It's a negative value, so it's getting larger and larger or closer and closer to 0. So when we take the derivative, we see the sign is what we expect, right? So we take the derivative of the velocity term. We got -2 as my constant. Negative 0.05 again is from the chain rule piece, e to the negative 0.05 t. So we get 0.1, positive 0.1, e to the negative 0.05 t. So here's our graph. The acceleration initially, so the acceleration is connected to the rate of change of our system, our velocity term, right? So initially there's a large change, and then it tapers out at the end, right? So same exact logic, just a specific application that's showing you how to apply the derivatives. Here we use additive, we use chain rule, and we use exponential. In previous problem, we looked at trig. So you see all these different mathematical tools are used in real physical systems. And these are just dummy examples that give us that perspective.